All right. So, obviously I'm not First Vice President Dale Parton, but since he is up in Gladwin, hopefully enjoying the skies, but quite possibly getting rained on and worse, he delegated me to be your host for this part of the show. So tonight we're going to learn about the GAIA mission. Now this is the ESA space probe that is the successor to the legendary Hipparcos, the satellite that in the late 80s and early 1990s mapped the sky as it had never been mapped before. Of course, now we are in a whole new generation, or rather many generations away in terms of the sophistication of the space probe, and GAIA promises to teach us more about the galaxy than we've ever known before. Here to tell you about that is Jeff MacLeod. He's a cartoonist, and he will be treated to examples of his work. He's been obsessed with space his entire life, with a special place for NASA, cosmology, and Richard Feynman, everybody's favorite physicist.
Gotta love Feynman.
Yeah. And like Feynman, he likes fun. As in his free time, he's an artist, juggler, and a unicycling street performer, and he may be demonstrating that.
Yeah.
So this promises to be a great one, so let's give it up for Jeff.
Thank you. Never got into the drawing. But anyway, this is my first presentation for the Astronomical Society, and this came about by making a rookie mistake of sitting too close to Dale at the Red Coat Tavern. So if you're new to the club and you don't want to give a talk, kind of steer away from him. So we'll be talking about the GAIA mission, and basically, as she said, it's going to be mapping the Milky Way in 3 dimensions to unprecedented accuracies, down to 20 micro arc seconds, and we'll go over that a little bit more when we get into it. But basically, we're going to talk about how you go about creating a 3-dimensional map of the galaxy. And basically, the first thing you need to do is build the most accurate 2-dimensional map that you possibly can, like a star chart, and then by adding parallax measurements, make all of those observations 3-dimensional. So we'll just get into, you can go to the next slide. Here's some just really simple mathematics. This is stuff you should have all seen before, just basic integral calculus. No, that's a joke. We're only going to be doing differential calculus. Measurement astronomy or astrometry is pretty much determining 2-dimensional positions of the stars on the celestial sphere, which can be converted to a typical star chart. This is actually a picture of the meridian scope from the Detroit Observatory in Ann Arbor. It's from like the 1880s or something like that. It's really old, a really cool piece of machinery. But basically how this works is it has a fixed azimuth mount, and it's pointed directly at the North Celestial Pole. So this is also known as a transit scope. As stars pass the line that this kind of traces out in the sky between the horizon and the North Celestial Pole, by knowing the sidereal time of the transit, this actually has a crosshair in it. You can convert that into a right ascension, and by knowing the angle, convert that into a declination. And you do this over and over again to multiple stars, and you start to build a large catalog. These were also used as timekeepers 100 years ago, before we had atomic clocks and everything. So, next slide. Another technique for getting 2-dimensional angular separations of stars is relative astrometry. And this technique uses a single scope taking a picture of a target star over the course of years. But there's some issues to this technique. If all of your background stars are moving, say they're one spiral arm of the galaxy that's rising or falling, you have to assume that they're stationary, and so your motion of your target star might really not be as accurate as you think it is. Another issue with this technique is you want really far away background stars and a closer target star. And then it gets difficult to get similar magnitudes of stars, so you don't have problems with exposures, all that kind of stuff. It's also completely impractical for a full sky survey, so not what we want. Go on to the next one. Just real quickly, this is known as multi-channel astrometric photometers, but basically what this technique does is it passes a fine grid across the optical plane of the telescope, which blocks the starlight at very precise intervals. And so by looking at where those modulations in light are, the separation in two stars can be determined in one direction. So then you have to then do a measurement 90 degrees to get a second dimension. That's kind of an older technique that was used. You can go to the next one. Interferometry, we're just going to blow right past it. The only reason I bring it up is it was a technique that was going to be used on the GAIA craft, but because of advancements in digital technology or digital imaging, it wasn't used. But basically this uses electromagnetic waves to determine angular separations. That's really, and interferometry can be a lecture on its own, but Dave Bailey would have to give it. Next one. So those were some astrometry techniques of determining two-dimensional separations on the celestial sphere to create star charts. Then what we need to do is to gain a distance away from them through parallax measurements. Parallax in a nutshell is the change in an object's position due to two viewing angles. You can demonstrate this by putting your fingers together and looking past them, and you see the floating finger. Everyone kind of did that in middle school. That kind of takes advantage of you having two eyes. That's actually how we determine depth, is through parallax in our eyes. And I kind of refer to that as the basis of parallax, the separation of your eyes. And for astronomy, there's a couple of different means that we can use to create a basis of parallax. The first being geocentric parallax, which actually uses the Earth spinning on its axis to create two different positions. You take a measurement at dusk, and then you take a measurement at dawn. You're roughly on the other side of the Earth at that time. This can only be used for determining distance to terrestrial planets and solar system asteroids, but it's really not large enough to get you to the nearest stars. What's shown here is heliocentric parallax, which is a much larger basis of parallax as the Earth goes around the sun. This was actually the first reliable way of determining distances to nearby stars, the first being made in 1838 using what's known as a heliometer. And a heliometer is pretty much a specialized scope which the primary lens is actually cut in half, and one half is set onto a hinge that can be very precisely angled. And so through that scope you get a double image, and you can look at a two-star system, not a binary system, but just two stars that are close together. And you can set that one lens so that the positions of the stars coincide over each other. And then by doing that measurement again, you hope to measure a different angle, and that'll give you a slight parallax of the closer star. That was really the first technique in determining distances to nearby stars. If you go to the next slide, we'll cover what a parsec is. You may be familiar with a parsec, famously being misused by Han Solo in Star Wars. It is not a unit of time, but a unit of distance. The reason I bring this up is because a parsec actually comes from the word parallax second. If you don't know anything about how we break down degrees in astronomy, every degree is broken into 60 minutes. Each minute's broken down into 60 seconds. And then seconds are broken down into even smaller increments that we'll talk about a little bit later. But when a star has a parallax of 1 arc second, which is 1/3600th of a degree, it is 1 parsec away. Another way of thinking of this is how far you would have to go from the sun and the Earth so that the sun and the Earth are 1 arc second apart from each other. And it turns out to be somewhere around 3.26 light years. The parsec isn't really that well known to the general public, but for astronomers, it's a more useful number to them, because if you know how many parsec away it is, you roughly know what the parallax of the star is, and vice versa. Whereas converting from light years to parallax is it's just a more messy equation. So far, all the techniques that we've talked about are ground-based techniques. And so the question might say, well, then why did we send this vastly expensive space probe when we could have built one of these things on the ground? And there are some crucial advantages to going to space. One being mostly that you're not in the Earth weather pattern. You don't have the atmospheric turbulence that you have on the Earth. You have better thermal stability. When you're talking about getting down to beyond an arc second into milli-arc seconds, which is thousandths of an arc second, any change in temperature can change the geometry of your telescope enough to affect the data. Another thing is there's no gravitational distortion. You've got the moon flying overhead. You've got groundwater moving. Also, you're going to be able to see fainter stars in space, also due to the fact that you don't have an atmosphere. The number one reason is there's no clouds. So let's just get out of the weather altogether. So you can go to the next one. That brings us to the Hipparchus mission. Now this was the first dedicated space mission for astrometry and parallax measurements. As Diane said, it was launched in the late 80s. It was actually 89. It operated for about 3 years. Now, the optical technique that this satellite uses is known as wide-angle astrometry, and we'll get into that a little bit more when we talk about GAIA, because they actually share the same technique. Some notable things about Hipparchus is it kind of had some problems early on. It was supposed to be sent to a very nice high orbit, close to geosynchronous altitude, but the apogee boost motor that was supposed to widen that orbit out never went off, and so it remained in this highly elliptical orbit that took it in and out of the Van Allen radiation belt. And mission scientists were pretty worried that it would damage the craft and pretty much cripple it. Fortunately, it was a little bit more radiation proof than they had anticipated, and by shutting it down in certain systems when it went into that radiation belt and then powering it back up, they were able to collect data 60% of the time and actually meet all the criteria that they set out to do. The goal for the Hipparchus mission was 120,000 primary program stars and some 400,000 secondary stars to a lesser degree of accuracy. Hipparchus achieved an accuracy somewhere around 2 to 4 milli-arc seconds, which is 2/1000ths of an arc second. Some other accomplishments of this telescope is it helped predict the impact of Comet Shoemaker leaving 9 onto Jupiter. It also discovered many variable and eclipsing binary star systems. It changed our understanding of the cosmic distance scale, making the universe larger and younger than was thought of at the time. So, you know, these kind of missions really do full-scale stuff beyond just simply mapping the area around them. So you can go to the next slide. This kind of just gives you a sense of scale. That might be Bob Tremblay, I'm not sure, holding the entire satellite up with just his left arm there. I think that's pretty impressive. So not a small spacecraft by any means. So you can go to the next one. We had to wait 24 years for the Europeans to pick the ball back up with another dedicated mission. NASA tried to do missions. There was the FAME mission and the SIM mission. Both were canceled due to cost and pushback after pushback. It's really a sad story that we just don't even need to get into. What GAIA will do is it will catalog 10,000 times the amount that Hipparchus did at 40 times higher precision. So this is not a, let's do double what we did before. It's not even tenfold. This is a massive step forward. So it's a huge technical achievement, and the data that we're going to get from this, for my money, is going to be stupendous. It's probably important to mention at this time that this is not an imaging scope. This is not going to take beautiful images of the galaxy like the Hubble Space Telescope or the James Webb Telescope. What this scope does is just create raw data that then needs to be processed on the ground and turned into useful information. So in the public side, this is probably not ever going to get the credit that it should, but in terms of the scientific payoff, I think this is really going to rival the Hubble Space Telescope in what it gives us. So the basic mission plan, there's some things here, and we're going to kind of go over those. 1 billion astronomical objects, which sounds like a lot, especially compared to the 120,000 that Hipparchus did, but that's still only 1% of the Milky Way's population of stars. So the most accurate, largest map of the universe will be just, or of the universe, of the galaxy, just 1%. But when you think of a map of the United States, it's probably less than 1% of what's actually there. I mean, your house isn't on a map of the United States. Wide angle astrometry. Basically what that is Gaia has 2 telescopes, not just one. And they're separated through a large angular separation, which is known as the basic angle. In Gaia's case, it's 106.5 degrees. And with this technique, basically how it works is you have 2 telescopes that are pointed in opposite directions, roughly. And when telescope 1 sees a star over here, it ties it in to a star and knows that they are exactly 106.5 degrees apart. But now as the spacecraft rotates, it sees this star again and ties it into a star over here. Then it continues to rotate, sees this star, and ties it into another star. And it just goes around and around. And what this is doing is taking advantage of the simple fact that no matter how many units you break a degree down into, you can just keep breaking into smaller units. It always adds up to 360. And so as this goes around in all directions, the measurements themselves can be used as a referencing point. So this gets rid of all of the issues of small field or relative astronomy that we talked about earlier, where if your background stars are moving and you're using those as your base points, you're not going to notice that shift. Well, because this is tied into stars over here, over here, over here, even if those stars are moving, you're going to notice every single bit of motion. The whole galaxy can't all be moving in a way that you won't be detectable. It's kind of hard to explain, but so I think we can go to the next slide. So Hipparchus was kind of just buzzing right around the Earth, but Gaia is going to be sent out to the Earth-Sun L2 point in what's known as a Lisa-Joule orbit. And what this does is avoids the spacecraft ever falling into the shadow of the Earth. And that orbit was chosen for thermal stability mostly. You don't want the telescope going into the shadow, cooling down, coming back out, heating up. Also, you're constantly collecting solar energy. The next slide will zoom in to kind of the orientation of Gaia. So we see here the 2 lines of sight of the 2 separate telescopes with a basic angle between them. Perpendicular to that, we have the satellite spin axis. Now that spin axis is always going to be at a 45-degree angle to the sun. The spin rate of the spacecraft is once every 6 hours, so 4 rotations per day. But it's not only rotating, it's also precessing, or it has a slight wobble to it. That cycle lasts 63 days. So that over the course of 63 days, this telescope will see the entire celestial sphere. Over the course of a 5-year mission, it's going to see that entire sphere about 70 times. And through that, you get kind of an averaging effect. So we'll go to the next slide and we'll zoom in right on top of the spacecraft. And this kind of shows you the internals and some components that we'll talk about. So these are, again, the 2 lines of sight of the telescope coming into the 2 primary mirrors, 2 secondary mirrors, 2 tertiary mirrors. These are the 2 combining mirrors, 2 fold mirrors, into the focal array. So what this telescope is doing, you've got 2 images that are then being combined and viewed by 1 detector. And we'll talk about how that's done in a minute. Some other components that we'll just briefly talk about: the Sunshield, what you can't see, the antenna on the backside, the optical bench, and some other things that we won't really talk about: the thermal tent. It's just a tent, you can get one at Walmart. Next slide. So This is the optical bench. This is the main backbone of the spacecraft. From the outside, it looks like a cylinder, but that's just the thermal tent. It's just a cover. This is what's actually going to support everything useful to this spacecraft. And you can just go to the next one. We'll see it a little bit further along in the assembly process. So I like pictures like this to just give you a sense of scale. This is not a small satellite by any means. This is made of silicon carbide. There's 19 individual pieces here. You can see the two primary mirrors up here, and right here is where the focal array is actually going to be mounted. That material was chosen for thermal stability. Thermal stability is pretty important to this mission. GAIA is meant to be operated at about negative 150 degrees Fahrenheit. So you can go to the next one. This is the Sunshield. It's actually the deployable Sunshield. So here's it kind of them fiddling around with it. Also another awesome picture for the sense of scale of this thing. 34 feet from end to end. And if you go to the next slide, we'll actually see it in a deployment test. So this Sunshield is actually folded up when the craft is launched and then deployed into space. You can see here, these are the actual solar panels. So it's not really a solar collecting panel, it is a sun shield. And if you think about it, we'll go to the next slide. When this thing is deployed into space, it's going to be turned at a 45-degree angle to the sun. So if you imagine sunlight coming in at a 45-degree angle, I mean, sun is just barely missing. So this is really as small as you could possibly make this shield and still protect the craft from any solar ray or heat and radiation. That is the sun shield. We can go to the next one. We'll cruise on through this. So this doesn't look like a typical antenna for a spacecraft. This is what's known as a phase array antenna. This was chosen because a mechanically driven antenna will cause too much vibrations that will just completely throw off the stability of this craft. I just like to quickly point out how proud this man is, okay? You can go to the next slide. I'd be proud too. So this is the back side of the antenna, and we'll talk about just kind of how it works. All of these are individual radiating elements. And how this antenna works is these radiating elements produce interference amongst themselves. And so the interference in that wave pattern actually guides the beam. This was chosen because GAIA needs a very high download rate. It's going to be downloading information to Earth 8 hours every day. Because of the huge volume of data that this scope is going to be taking in, you just can't build a storage device to hold it all. Also, it would be very dangerous to trust something to hold that volume of data for a long period of time. So you want to be just constantly receiving data over the 5-year mission. This is a picture of the primary mirror. It's also made of silicon carbide for thermal stability. He's kind of doing the fast photo where he makes it look bigger than it really is. It's about just under 5 feet long and 1.5 feet wide. You can go to the next one. So this is the real heart of the spacecraft. This is the focal array. This is where the 3 main instruments for the craft, and this is really how they're achieving this map-making feat. You can go to the next one. I'll give you a picture for scale. I think these guys are just photo-opping. I don't think they're actually working, but so there's them putting, these are known as CCD or charge coupled devices, and they are the detectors for the craft. There's 106 on this panel. This is the largest focal array that's ever been launched. Essentially, it is a 1 billion megapixel digital camera. So you can go to the next slide. And so this is just kind of an overview of the layout. And as I mentioned, the spacecraft is constantly rotating. So as light comes in, it goes from one detector to the next across the focal point. So, find my place here. All of the detectors are basically the same, but they're dedicated to different instruments. There's 2 basic angle monitors. If I have time, we'll get to those. There's also 2 wavefront sensors. But the crucial instruments are the sky mapper detectors the astro or astrometric mappers, the 2 photometer collectors, and the radial velocity spectrometer. Oh, no, sorry, too soon. We'll get to that later. I'm on this for a while.
I got it.
Because there really just isn't any useful pictures of this stuff. So the first row is the sky mapper, and this is the crucial, I kind of thought someone would ask how you have 2 telescopes that are viewed by 1 camera and you possibly keep these 2 images separate. And the sky mapper is what does that. There's a physical mask in the telescope itself, so that telescope 1 can only fall onto this row of detectors, and the other telescope's light can never fall onto this row of detectors, and vice versa. So every star is either cataloged by SkyMapper 1 or SkyMapper 2. That assigns the star a pixel window, which has to do with the magnitude of the star, and this helps for overexposure and that kind of things. So all of the subsequent instruments use this data to know what the heck they're looking at. You can notice that the main portion is the astro mappers, and this is where the real astrometry is being done. These instruments are just dedicated to determining angular separations and locations of thousands upon thousands of objects. Every single object is being tied into thousands of other objects from the opposing telescope. So in this way, you're getting the separations of individual stars in a field, but then over the course of the 5-year mission, you're looking for tiny motion. The next time it sees that star, it's moved slightly as compared to a star on the other side of the telescope. And what this does is, in data processing on the ground, you can process this into a motion that might look something like this. What these tiny loops are the actual parallax motion of the star from the telescope going around the Earth. When you process that data out to get the distance to the star, you get what's known as the proper motion of the star. This is still just 2-dimensional though. This is basically a moving star chart. Now you can go to the next frame. When you get to the blue and the red photometers, before the light hits them, they go through these prisms, just like any prism on Earth. It separates out unwanted light, and we're only interested in looking at certain wavelengths. Between the 2 of them, they're going to be seeing the entire visible light spectrum and some of the near infrared. And the kind of information, well, let's just put it this way. The first instrument is the where, which is nice, but we really are pretty concerned with the what. And this is the instrument that's telling us the what. What are we looking at here? And that's crucial when you actually want to do science with this map. I mean, a map is nice, it's good, but you need to know what kind of stars you're looking at. Are these young stars, old stars, large stars, to identify different stellar populations. And that's really when we get into galactic evolution. So the kind of things that this instrument is going to give us is temperature, mass, age, and chemical compositions of every single star that's being observed. You can go to the next one, we'll go back to the same image. So then the light falls onto the radial velocity spectrometer, and basically what this instrument is doing is measuring red shifts or blue shifts to get the velocity of the star. Is it coming towards us or away from us? And what that does, which is crucial to an accurate map, is it turns this 2-dimensional line into a 3-dimensional line. That really helps in your accuracy. This is absolutely necessary to an accurate map of the galaxy. Next image, before it actually gets there, it goes through what's known as the optical module. If I could tell you how this works, I wouldn't be here. I'd be at Caltech or something. I just think it's a really cool picture. I just don't have the time to try to figure out how that works. It's a grading plate, few silica lenses. It's really neat. And basically, I can tell you what it does. Maybe Dave Bailey can explain it to you. let's see, it takes out the main aberration in the off-axis field of the telescope. Okay, goodness.
Looks like a lot of optical glass.
Yeah, pretty much. It's just some really cool sciencey stuff. All right, next slide. This is a video processing unit. There's actually one for each row of detectors, and you can just go right to the next slide. That compresses data before it hands it off to the data handling unit. This is the solid state storage device of the spacecraft. I wasn't going to mention it, but I started thinking about it, and if anything happens to this over the course of the mission, it's over. I mean, this has to work, it has to store the information before it sends it off to the antenna to be downlinked to Earth. It's got a capacity of around 960 gigs, which is actually a lot for a space-based platform. I mean, you can get a hard drive that's bigger than that, but it won't be anything like this. But that's nothing compared to the overall volume of data that they're going to have over the 4-year mission. They're looking for about 200 terabytes of data, which equates out to about 200,000 DVDs. And if you think about how much data a DVD can hold when you're not talking a movie, you're talking compressed image, not really images, just information, ones and zeros, just stupendous amount of data. So we'll go to the next slide. These are the two basic angle monitors. How am I doing on time?
That's fine.
I'm
Fine.
I'm doing good?
You got lots of time.
Oh, okay, good. That means lots of juggling. All right, so the basic angle monitors, to make them as simple as possible, these are mounted on the optical bench, and they send a laser beam to the two primary mirrors that then go down through the normal path of the telescope to the dedicated detectors. And what these are doing, those detectors are just watching that laser beam to see if it moves slightly. And if it moves slightly, it means that there's a change in the angle of those two mirrors. I guess this is a good time to break down how detailed GAIA is trying to go. An arc second is 1/3600th of a degree. That's 1 arc second. A milli arc second is 1/1000th of an arc second. A micro arc second is 1,000th of a arc second. So it is, I don't even know what this is called. What's it? 1/10,000th of an arc second, and they're trying to get down to 20 milli arc seconds. Which then, if you divide that by 3,600, it's, I wrote it down here because it's just ridiculous. It's 2.7 to the -9th of a degree. So this is a very, 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 very small degree of angular separation. At those levels, you just can't build anything rigid enough to stay at that particular angle. So you need to monitor it.
In terms of parallax, what does that turn into in terms of the distance away that it can resolve?
Boy, they're trying to get to within a 10% degree of accuracy out to the galactic center,
Okay.
which is like 33,000 light years. And there's a slide on that a little bit later that will show they're actually, to a lesser degree, going to be going beyond that.
So that degree of angular resolution will allow them to measure
Yes.
that distance and be within the...
Yeah, to about 10%.
Right now,
Accuracy.
we can do it with accuracy of about 360 light years.
Yeah, that's
Yeah,
pretty big
this
difference.
is this is a whole, this is like 2 orders of magnitude
Maybe
further
more
than,
that.
yeah,
More than
it's
that.
stupendous. So I don't even know what the next frame is, so, did we cover the basic? Yeah, we covered the basic angle. It's expected to change by about 7 micro arc seconds over a typical spin period. And so basically, that information is tagged onto every single image. How far out of alignment was the basic angle? This is a close-up of one of the CCDs. Somebody, not me, could talk for 45 minutes just about these things. They're pretty interesting when you get into how much had to go into these as far as radiation resistance and just the kind of things that they're trying to do. So that really covers all of the components and instrumentation of the scope. So what I'll talk now is a little bit about the processing on the ground that's going to be going on. All of the pixel field coordinates have to be converted into angular field coordinates to create this map. And this is done through geometric calibration, and there's a lot of things that go into correcting this information, as far as the calibration of the focal plane itself, instrument attitude, and the basic angle that we talked about, also chromatic shifts and relativistic light bending. So there's a lot of things that have to be kind of dialed out of this mess of information before you get anything useful. And also the kind of the law of averaging is how they're going to be able to get this kind of accuracy. And this is going to consist of about 400 scientists across Europe that are going to be responsible for handling this huge volume of data. And it's going to take them a couple of years.
They
And
can
we're
all,
really,
you can put them all, they can all stand on that chip.
You sent me a message saying that Gaia had already discovered its first supernova. In about a year's time, they're going to be hoping to find a couple every day. So, and that happens through, once you really start processing the data, every time you see the same patch of sky, you're looking for new supernova. So basically, what we get to now is, I guess you can go to the next one, is what's the point? And if I really have to tell you what's the point, you're probably in the wrong room. But anyway, some of the goals that they're trying to get is astrometric and kinematic properties of our galaxy. And this includes also the detection of some 500,000 quasars, which are the feeding, or at least we think the feeding centers of young galaxies way off in the distance. And those also help for calibration because they are very bright objects very far away that don't move very much. There's also like an international reference system for this kind of measurements that use 212 known quasars as very stable background points. Gaia is also going to be uncovering thousands of new asteroids in our own solar system, especially ones that are difficult to detect from the ground, ones that are between the sun and the earth. And it's also going to refine orbits of ones that are already known. So because the kind of mission that this is, mapping the Milky Way is the primary mission, but we're also going to be doing intergalactic stuff, and we're also going to be doing stuff kind of in our own neck of the woods. This image kind of shows the precision kind of dropping as you go further away. So here's the detection range of like Jupiter-mass planets, a far distance, but not far in the total. But then as you go out to 20 kiloparsecs, which is 20,000 parsecs, you start really dropping away quickly. So it's important for me, at least right now, to mention that this is not a stagnant map of our galaxy like you would see in a star chart. This is a moving map. And so what you can do with a moving map is you can actually run it forwards and you can run it backwards. And the more accurate that map is, the farther you can play those games in reverse or forwards. So we're going to be able to track different populations of stars further back in time than we've ever been able to do. And we're also going to be able to play them forward further than we've ever done. And so this really helps us when we try to ask questions about galactic evolution and where we're heading. Are there a group of stars that have a good chance of kind of causing problems for the solar system in the next, 10,000 years? Those kind of questions will be answered. That's pretty much it. Any questions?
Sure.
Yeah.
So one thing that blows my mind is not just the resolution that you list there, the 2.7 times 10⁹ degrees, but the fact that in terms of parallax, that's as Ken was chiming in, That's an incredible increase over what the current
Yes.
measurable, because parallax has always been kind of limited by our ability to actually measure some kind of shift. But
It's Cepheids.
the other awesome thing though is in terms of proper motion studies.
Yes.
Proper motion studies are usually the kind of thing where, you know, you compare plates taken 50 years ago to measurements
Yes.
made today. It's like, okay, over those 50 years, we've measured that star is moved.
Yeah, and I tried to keep
And
a lot
that
of the
resolution.
technical details out
Yeah.
of the talk, but I mean, they're, and I even took them out of the sheet altogether. But as far as the radial velocity that they're trying to get, I mean, it's down to like 5 kilometers out to some ridiculous, like 10,000 light years or something
Yeah.
like that. And also,
Of course, there's two different motions. There's moving
yes,
towards
exactly.
us,
And
the
you
radial
really
velocity
do need
towards or
both
away
of
from
them.
us. Yeah.
One is completely useless.
Versus
to-
proper motion, which is
Exactly.
moving within the plane of our field of vision. The awesome thing is that they're going to be able to figure out, I mean, if they're able to measure all these things with this kind of resolution, they can tell you where those stars will be at X time in the future.
Exactly, yes.
And really have a living model
Yeah,
of
and you
not
know,
just 3D, but living model.
One of the things that was in my earlier kind of run through for this project was, you know, that we have very accurate maps of Earth, and then if you do a Google search for a map of the universe, it's actually easier for us to map the entire universe than it is for us to map our own galaxy. The Sloan Digital Sky Surveyor has mapped galaxies back to, I think,
300,000 years.
oh, it's way further. It's in the, it's
300,000 years.
after the Big Bang, yeah. I mean, and so, and that's done through a completely different technique that's just kind of easier to do. And plus, you're at nowhere near the same accuracy. You're talking about whole galaxies, not individual stars. And so we always see these great images of our Milky Way. And, you know, when we watch PBS specials, we zoom to the hearts of these, you know, bustling centers. And these are all just graphics. We really don't know with any level of detail what our actual galaxy looks like.
There's another factor involved, like when we look at a star like Deneb, for example, the distance to Deneb is somewhere between 1,600 light years and 3,200 light years distance, because there's no Cepheids in the area, so we can't measure anything.
Yeah.
This thing will take care of that like that.
Yeah. It's
Amazing.
I really hope that it gets the credit that it deserves.
Well, you brought up how it compared to Google Maps, for example. Knowing to high resolution both the radial velocity and the proper motion, it would be like Google Maps where it's like, I don't just want to look at Paris, I want to get street view of Paris in 1900. I want to
Yeah.
get street view of Paris in the year 2478. You
Yeah.
know,
I mean,
to
it'd be
be able to project forward and backwards
I
in
mean,
time.
it'd be similar to having, you know, like a map of the United States that's also telling you motions of plate tectonics of the Earth, and, you know, I mean, it's a very dynamic view that we're going to get here. And also, to me, it's vastly important that you have the what. It's not just locations that they're concerned with, it's what are you actually looking at. And really, one of the things that they're kind of most driven towards is those more distant, older stellar populations within the galaxy. And you need more, how do they put it? You need more time and more accuracy to really understand those distant populations. Yes, you moved.
So we actually have a question from Facebook. And that
We have a
is-
Facebook?
We do have Facebook.
Oh.
So the question was, there was, after the commissioning of the telescope in May, there was a discovery of a straight line problem and also an ice buildup problem. And it was basically, do you know of any strategies that they're taking to deal with the straight line problem? And what is the impact going to be on the size of their?
Well, I will tell you this, because I think that you brought this up about a month and a half ago or something to me, that they were having their first kind of bug that crept up on them. And The Europeans' GAIA blog mentions nothing of it, so I don't really know. I kind of focused on the construction, and I just kind of, because otherwise I just keep adding in more and more things.
Yeah.
So at a certain point, I'm like, I'm not even going to look at what's going on with this thing. So yeah, I really can't answer that. So
I'm not sure that they can
Facebook-
answer that yet either.
I'm sure Facebook has a meme, so just
There's also, one of the funny things about it is that they actually had ice buildup on various parts, which they expected on the mirrors actually. So they had frost on the mirrors just like we do, and they turned on the dew heaters. So we actually, so the GAIA spacecraft is outgassing. So,
huh.
which is kind of a funny concept.
Yeah.
You mentioned that the craft is at the Lagrange point,
Yeah.
sort of behind the Earth. What it was about what 1.5 million kilometers away.
Yeah.
And the reason for that is the stability of
yeah.
orbit and stuff.
Yep. Thermal stability is really the main attractor to that kind of orbit, because you don't have to worry about falling into the shadow of the Earth. Whereas where Hipparchus was being around the Earth, at some point you're gonna fall behind it.
So as the Earth goes around the sun, the craft will be going around with us, and
Yeah.
it's set to compensate for that.
Yeah, I'm not hugely into how you'd have to talk to someone else about how the L points really work, because I've never really understood it completely. But yeah, it's pretty much it's actually orbiting around the L2 point, and so it's just it's those gravitational sweet spots where you're just kind of balanced, and so it will always be behind the Earth relative looking to the sun. Yeah.
I'm not
Yeah.
sure if they've looked at this much, but wondering what effects gravitational lensing has on these kind of measurements.
Well, it's something that has to be corrected for.
Yeah.
And so they are looking for it, and I guess it's the kind of thing that they hope through determining the parallax to different objects, you're going to be able to identify which objects are causing that lensing and then correct
So they
for
are
it.
looking at
Oh, yeah.
they're
Oh, yeah.
compensating for that.
And they're also going to be confirming Einstein's theories to a higher level of precision. That's another goal of the mission, is that you're going to be testing Einstein's theory to a higher level of precision.
So given this,
No, you're
given
fine.
this kind of precision, do you know how they're controlling thermal effects on these mirrors? And is this
There are so
cryogenically-
many components that I didn't get into.
It's probably some kind of a cryogenically controlled type of thing, I imagine.
They
Well,
actually
they're
have
not
heaters on the mirrors.
Yeah, because they're
They do have heat.
yeah they're only trying to have an environment of negative 150 degrees.
So they hold it.
So out in just yeah, the Sunshield is the main
Yeah. Interesting.
cooling agent, I guess you would say. Once you're blocking the sun adequately, you tend to drop off in temperature. Do you have a question?
Yeah, I'm sorry that I came in late.
No,
to the
you're
meeting.
fine.
I
I'm just
had
gonna get
stuff
into my
to do.
work chair here.
All right, I was thinking about the problem with, so is it based on pulsar mapping that you guys are using, or just?
Well, the measurements themselves will actually serve as the referencing points, but they're also going to be detecting thousands of quasars. And the quasars are really the best referencing points because they're the brightest objects at the furthest distance.
Right.
So the main mission is to examine our galaxy,
Yes.
but as a bonus, we get to discover tons of supernovas
Yes.
in other galaxies.
Tens of thousands of supernovas are suspected to be detected. And the first one they detected, I believe, was a type 1A.
Yep. And quasars in very distant, very early galaxies as well. So
Yes.
Kind of a multifaceted question. So just a quick back of the envelope calculation. It looks like compared to contemporary methods for measuring parallax, it's about 5 orders of magnitude better.
Yeah, that's,
So there was somewhere I was going to go with this.
I believe Hipparchus went down to 2/1000 of an arc second. And so we're going, you know, that's 3 orders of magnitude right there, going down to 20 micro arc seconds.
So I guess my first thought is this dramatic improvement, this dramatic jump. What do you think is the enabling technology that's doing it? Is it the CCD?
I actually sent
technology?
a message to one of the project scientists because Dale asked me the same question and I couldn't answer it.
Yeah.
And then he sent me an answer and I couldn't read it. I asked him to dumb it down for me as best as he could. And basically the answer he gave me was pretty much over the course of the 5 years, seeing the object 70 times allows for accurate averaging to be done. And that's
Okay.
basically
So it's
how
seeing
they're
it
doing
on
it.
every rotation.
Yes,
just-
and that number of 70 times to me really, it isn't that accurate because it's going to be observed 70 times, but I think what they mean by observed is that it sees it through the first scope, then it sees it through the second scope. But also, with that precession cycle, when it comes around again, that same star is probably still in the field of view, depending on where it is. There's a little bit of an overlap there, and so you're going to be seeing things a lot of times.
Like compared to other kinds of measurements I'm familiar with, is that if you do a lot of data averaging over a wide collection, you know, the signal to noise drops by a lot,
Yes.
and that improves a lot of precision.
Yes.
So I think a lot of like I don't know, NMR, X-ray methods that I've used in the past, where it's like you're just averaging over a long, long time, you know, collecting a lot of data points, and then suddenly that signal becomes
Right.
a lot more, you know, a lot stronger relative to the noise. Wow, okay. Oh, go ahead.
I'll come back to you.
Just a quick one, Jeff. From what's described, it's not gonna, doesn't sound like to be useful in identifying any exoplanets.
Oh, God, I didn't mention that? No, yeah, there's going to be, they're hoping to discover between 1,000 and 2,000 extrasolar planets over the course of this mission. Yeah, there was a mention of the Jupiter size limit, but yeah, they're going to be discovering, because in that wobble, there might also be, so that's the parallax wobble, but there could also be a planetary wobble in that data somewhere else. And so by taking the parallax out, then you're just going to be seeing the planetary wobble, then you discover the planet take to the proper motion.
Down to Jupiter size.
No, there was a limit to how far out it could see Jupiter-sized planets, but it all depends on where it is. If it's close to home, it'll detect fairly small-sized planets. I never heard it say Earth-size, but it wouldn't be out of the realm of possibility. But yes, many planets.
Another question I have is, you said that we have tons of data coming off of the spacecraft itself. Is there any way that NASA is helping out with the data itself, or is it just European?
No, I don't think we're a part of this at all. There is a slide. If you want to go, it's kind of it's the one that has just the overview and kind of a.
Is it like 40 European companies?
Yeah, and 15. Let me just keep going back. It's on there somewhere.
And are they publishing the raw data?
Yeah.
I know the U.S. institutions tend to be really good about it.
There,
and
Yeah,
that
this
one.
one. Forward
Forward,
one back.
yeah.
So yeah, 50 European companies, 400 engineers, 15 projects involved, which is all the different manufacturing pieces and elements.
Pretty much our hands are.
And if you ask me personally, it seems like to me the Europeans are doing the really exciting stuff right now, and other countries are doing things that we've done, but it's exciting for them, and we're just kind of, I don't know, we're just not
concentrating on.
We got some really cool projects. I mean, I'm really excited about the James Webb Scope.
Well, the web's funding is eaten every
Yeah.
time.
Yeah.
Yeah, it's pretty
Yeah.
much.
So,
Yeah, it killed the other
Yeah,
two
yep,
missions.
and dozens of
And
other
why we
projects.
can't get those dollars, I'll never understand. I actually read an article, this guy was writing about the Curiosity rover and the woman sitting next to him in Starbucks, because if you're a writer, you have to write in front of people. And the woman said, oh, that $3 billion price tag for Curiosity was such a waste of money. And so he got to thinking, he didn't know how to react to that. And so he started doing some research, and that year Americans had spent $14 billion on Valentine's Day. And so in comparison, he's like, so if we didn't buy roses and chocolate boxes and Care Bears, we could do 6 Curiosity missions a year or something like that. I mean, it's just crazy. Drop in the bucket. I mean, we should be doing a lot of cool things.
And the European economy is worse than ours.
Yeah.
Yeah, actually it is.
But their funding for space programs is not.
Yeah, they don't have the same defense. Never mind. Anyway, we spend a lot of money on defense that we don't need to.
You're talking about a solar parallax method in the beginning of the talk.
Yes.
I was wondering how much of an advantage we would have if we would have observatories on, say, Mars or some of the outer planets that could do this kind of work.
Yeah,
You know.
the larger your basis of parallax is, the better your technique would be. So theoretically, if you could get Gaia out to a Jupiter orbit, it would be even better. The problem is then it takes so long for you to make that orbit that you're waiting decades to get the same amount of data.
Well, even just Mars with
Yeah.
approximately 2 years longer
Yeah.
than Earth's a year would be. It's a bigger orbit.
Yeah.
So it's definitely more
Well,
than Earth.
it's definitely, my guess would be the funding issue of just sending something out there
Yeah.
makes the cost so much more.
Well,
Sending anything out.
Yeah.
you wait 12 years on Jupiter to get.
Yeah,
the-
exactly.
My slightly snarky response to Brian would be that, or you could just improve the resolution through technology to the point where you can just
Yeah,
keep it right
exactly.
here
Yeah.
and do everything you need to do,
Yeah.
which is basically what this has done with that kind of
Yeah.
angular resolution. Oh, one quick question I had. What's the magnitude limit in terms of detectable magnitude? for
I
a
believe
star?
it's down to 20th magnitude.
20th magnitude?
Yeah. And I took that out of the presentation, but there's actually a arc-second degree of accuracy per magnitude,
Oh, okay.
and it changes
That makes
based
sense.
on magnitude, but
So I
it was just way too much numbers that no one wants to hear.
Yeah, I think that'll actually be a bigger limitation than any of the resolution data
Yeah.
that we've presented, because, if a main sequence star, like our sun, how far away would you have to be from our sun for it to be
Yes.
20th magnitude, and the answer
Well,
turns
and
out to
that's a
be
huge
much
thing.
less
I mean,
than the
if you
angular
can see the
resolution.
entire, when you can see the entire galaxy, the only stuff you're gonna see over here is the brightest objects.
Yeah.
And so, but you're gonna be getting a good idea of the entire population really close in, and hopefully being able to just apply that kind of thought pattern to those other regions. So you say, okay, here there were this many, super mass stars, and so over here, there's the same number, so maybe there's the same number of M dwarfs and that kind of stuff.
You gotta contend with space dust too, I mean, dust gets in the way and it affects the magnitude,
Yes.
the apparent brightness, there's a lot of variables.
Yeah, and that's another reason why the accuracy goes down pretty steeply once you pass the galactic center. It's down to like
Right.
20%.
When are they gonna launch this?
This is already up.
That's already up?
Yep, it was launched in December of 2013. So it's been up for almost a year now.
Everything's fine?
Well, he said there's issues.
Yeah, there's a few issues, but there always are. So we're
Yeah.
not sure what the actual extent is. Were you going to do a
No,
grand
if you want-
finale involving?
if you want me to.
Maybe we should applaud his talk before we.
Well, we can.
Yeah, you know what? I commend you for asking all astronomical questions, because most people are all like, like, so how did you get into unicycling? But you guys didn't do that.
See, I think it would be best if you were answering questions while juggling
Yeah.
on a unicycle.
So that's too many things at once. So I can try to pull off some tricks for you here. I got a kind of a low ceiling here, so we'll just start off with some simple doubles.
All right, Jeff, what is the meaning of life?
The meaning of life is motion to me. Whenever I'm in motion, I'm much more satisfied with life, whether it be on top of a unicycle, climbing a tree, juggling. I figure I'm going to move while I can.
Indeed. So it's a, tell us. Ah.
Did you see that? I almost dropped one. There's some new tricks I learned, but I probably won't be able to pull them off today.
Will this be a requirement of all future lecturers to have to ride the unicycle and juggle?
Yeah, you may be setting expectations for yourself in the future.
It wouldn't be the first time I hit myself. So yeah, that's what I do on the weekends. I don't know what you guys do.
All right. Well, unless there are any final questions about unicycling, juggling, the meaning of life,
the
or
unicycle?
Just about anyone can learn how to ride a unicycle with enough practice.
but probably, I don't know if the liability policy for the library covers unicycling.
Yeah, you know, I didn't set off the metal detector, so I was happy.
I have a hard time with two
Just- you
wheels.
can- Don't, no, don't. Don't, cancel, just shut it.
Don't.
Done, we're good.
Just, yeah, you can just shut it, okay.
I know what to do with it.
You can just close them. That's what you do with Macs.
I never do that, I just shut it down.